How you doing? So for this problem, one of these is a possible electrostatic field. It wants to find out which electric field vector isn't possible. So for you to know electric field is possible, we know that the curl. Sorry, we know that the curl of the electric field has to be equal to zero. Um, so we want to take the curl of both of these electric fields. So for A, we have the curl is equal to K for our matrix. For the crosses, X, Y, Z, derivative respects to X, the derivative respects to Y, derivative respects to Z. And our elements, X, Y, 2Y, Z, 3, X, Z. So that is then just equal to K times X, and 0 minus 2Y, plus Y, 0 minus 3Z, plus Z, 0 minus X, stands equal to K, once you do the multiplication, minus 2XY plus 3YZ minus ZX. And since that is not equal to zero, and this one is impossible. Now we do the same thing for our second equation. So we want to take the curl. For this equation, we K, X, Y, Z, derivative respects to X, derivative respects to Y, derivative respects to Z. Now elements Y squared, 2X, Y plus Z, and 2Y, Z. That is then equal to K, X, 2, Z minus 2Z, plus Y, 0 minus 0, plus Z, 2Y minus 2Y, which can be further simplified to K, 0, K times 0, where K is a constant. So we know this is 0, so that verifies this is possible. So now the question asks us for the possible one to find a potential using the origin as a reference point, and then check our answer by doing the gradient of V. So we know to check the potential, we know the potential is equal to E, the integral E dot dl. We know E dl is equal to k y squared dx plus 2xy plus z squared dy plus 2y z dz. So for our first path, we call it path 1, which is on the x-plane. We know dz and dy both are 0. So we place that in the equation. So we get E dl is equal to k y squared dx plus 2xy plus z squared 0 plus 2yz 0. This equals k y squared dx. Therefore, it will equal 0. So for path 2, which is on the xy plane, we know that dx and dz both are 0. So for E dl, we have, and it goes 0 to y naught, 2kx x naught y dy. Then we have, take the constants out. And we have 2k x naught times y naught squared over 2, which ultimately leaves us with k x naught y squared, y naught squared, I'm sorry. And then for our last path, path 3, which is our y z plane, x is equal to x naught, y is equal to y naught, and z is going to be equal to 0 to z naught. So we substitute those in for our equation, and we get E dl is equal to k times y squared 0 plus 2xy plus z squared times 0 plus 2y z dz. And that's equal to 2ky z dz is equal to 2k y naught z dz. We have to integrate, so we get 0 to z naught to ky naught z dz, which is equal to 2k y naught 0 to z. Once we take our constants out, z naught z dz, which is then equal, once we integrate, to 2k y naught z naught squared over 2, which is then equal k y naught z squared naught z naught squared. I'm sorry. So we know the net potential. So UV x naught y naught z naught. So integral EDL. So we plug in what we got for EDL. It's x naught, y naught, z naught equals negative k x naught y naught squared plus y naught times z naught squared. So this is our final answer for our potential. And now we just have to take the determinant of that potential. So we get k integral respects to z xy squared plus yz squared x hat plus integral respects to y xy squared plus yz squared y hat plus integral respects to z xy plus yz squared times z hat. Which then equals k, so y squared, y squared x hat plus 2xy times z hat plus 2y z times z hat. Therefore, our potential is simply equal to our electric field, which also proves that our potential is equal to negative k x naught squared plus y naught z naught squared, which is the same answer that we got above. Thank you for watching this video.